So we're going to look at 4.5, and this is called exponential and logarithmic functions. I'm just going to abbreviate expo and log functions. And basically, this whole section is going to be about solving for x and solving exponential and logarithmic functions for x. And so we're going to learn several different techniques, how to find those. A lot of the times, and you're going to hear me say this a lot through this lecture, a lot of the times, every single one of these problems boil down to converting from logarithmic to exponential function. So make sure you are comfortable with doing that. We talked about that in section 4.3 and in 4.4. So please go back and review at least 4.4 from from the previous section to get a good handle on that. The first thing we're going to talk about is called the equivalence property. Equivalence. There we go. Equivalence property. And the equivalence property is the easiest way. This is the equivalence property. I should be more specific. Equivalence property for exponential expressions, for expo expressions. So the equivalence property for exponential expressions, and later on in this lecture we'll learn about the logarithmic, the equivalence property for logarithmic expressions. Those two are the simplest ways to solve for x in this entire section. So just real quick, I'm not going to write the entire definition. I'm just going to jump straight to the bones of it. It says if you have a base raised to the x power, and that's equal to another base raised to the y power, and I shouldn't have said another base, the bases are the same. So if the bases are the same, then that implies the exponents have to equal each other. And I'll do this double arrow. It implies x is equal to y. In other words, you set the exponents equal to each other. And we looked at this several times, a couple times throughout this entire chapter. Specifically, we looked at something like this. If you have 5 to the x is equal to 25, you could tell me the answers too. But to use this form here, make the bases the same. How do we make the bases the same? The base here is 5. How do we rewrite this so that way its base is 5? Well, 5 squared. So 5 to the x is equal to 5 squared. Since the bases are the same, that implies the exponents have to equal each other. So x is equal to 2. So you've been doing this. We've been doing this all along. It just now we're kind of formally writing it out. And let's look at a little bit tougher question. Something that you'll see on the exam. Example 1. I'm going to say solve on all of these, and it just means solve for that particular variable that's in that problem. Part A, let's say 3 raised to the 2x minus 6 is equal to 81. So it's a little bit different than this problem, but it's going to essentially work exactly the same way. And like in section 4.4, you want to be able to look at these problems and identify what you're going to be doing for this problem, how you need to rework it. So in 4.4 we looked at product and quotient and power properties, and how you should just be able to look at it and say, okay, this is what I need to do. So for this particular problem, you should just be able to look at it and say, this one is familiar, this one's easy, because let me rephrase that. It's not necessarily that it's easy. It's the first thing you always want to do when you're solving any problems in section 4.5 is try to make the bases the same. That is what it, if you try to do that on other problems, it's only going to work some of the time, very little of the time, but it's the easiest way to go about it. So here we know that we have to try to make the bases the same. So the base here is 3. And so we need to change this 81 somehow to make the base of 3. So that would be 4. So you would get 3 raised to the 2 minus x is equal to 3 raised to the 4th power. Now that my bases are the same, that means I can set the exponents equal to each other. So I get 2x minus 6 is equal to 4. And then we're on the home stretch now. This is something, we've reduced something that we're somewhat vaguely familiar with to something that we're very familiar with. So add 6 to both sides. So 2x is equal to 10. Divide by 2. And x is equal to 5. Now if you wanted to check yourself, how would you do it? You take this 5 and you plug it in here for x. And if both sides equal each other, then that will tell you that you got the correct answer. Alright, let's try another one, and I want you to try it by yourself. Alright, here it is. Part B. 4 raised to the 2x minus 3 is equal to 64. Okay, so give the video a pause and try to work it yourself. I'm going to start it right now. Alright, so we need to make the bases the same here. And remember, that's the first thing you want to ask when you're working anything, when we're solving for a variable. Can we make the bases the same? And here, the answer is yes. We can make it a 4. So we get 4 raised to the 2x minus 3 is equal to 4 cubed. We want to do this because now our bases are the same. That implies that whatever is in the exponents have to equal each other. So 2x minus 3 is equal to 3. Add 3 to both sides. 2x is equal to 6. Divide by 2. So x is equal to 3. And how do you check yourself? Take x equals 3 and plug it into the top equation. Alright. Let's look at this one. Let's call this one part C. Seven to the x power is equal to 60. Alright. So, what did I tell you about working these problems? The first thing you always want to try to do is you want to try to make the bases the same. So on the left here, my base is 7. Is there any way to make 60 a base of 7? There isn't. So we need to come up with a new way or a different way to solve these types of problems. And it just so happens you already know how to do it. It's just a matter of me showing you. And this section just takes some practice. And the more you practice it, the easier these will get. So just please don't give up. Keep trying. You'll get these eventually, because a lot of this stuff in this section we're doing you've done already. It's just trying to combine several things in one that makes it kind of difficult. But in the past, in last section 4.4, I said in the other sections, at least the parts that you could hear me, I was saying all of these problems in this chapter, or in here in 4.5 too specifically, all these problems will boil down to you having to convert from exponential to logarithmic form, or logarithmic form to exponential. So there may be several steps along the way that you have to do, but then the last couple steps, somewhere in there, it boils down to what we learned in the very first, or in 4.2, is converting from exponential to logarithmic form. Here, can you tell me which form we're in part C? Are we in exponential or logarithmic? We're in exponential. Go back and review 4.2 and look at the definition of exponential that was given. So to convert this to logarithmic, hopefully we're all good with that now. We know when we're converting from exponential to logarithmic, we're going to have a log in here and an equal sign. And so log, and then this is the little subscripts to base. So log base, what's your base up here? Remember, this is your base, 7, exponent, and then your what's left over, or your answer. So log base goes here, which is 7. And then remember, when we're in logarithmic form, what's over here is always our exponent, because that's what we're trying to solve for. That's the point of logarithms, is to get that exponent out of the exponent. And so that's there, and then what's left over is 60. Again, if you're struggling with that, go back to 4.2 and look some of that over. Alright, and that is your answer. X is equal to log base 7 of 60. And we can leave it there. Let's see. Let's try this one. It's kind of similar. Just a extra step here or there. And I encourage you to try this one by yourself. The faster or the sooner you can start doing these on your own, the better. Part D, 10 raised to the 5 plus 2x power plus 820 is equal to 49,600. That's equals 49,600. Alright, so the difference between this problem and part C, let's just see what's the same. Well, we have the equal sign, so let's start there. That's a good place to start. And then we have the answer, or what's left over here. So the equal sign and this is roughly the same, just trying to compare in general. Then we have a base here raised to a power with a variable in it. And then here's our base with the power in it. So the thing that's new here is this plus 820. So all I did was doing in this problem is, the only thing that changed was adding this 820 on the left side. And it just so happens that that 820 is an issue because we're kind of stuck right now. We can't do anything. Okay, so to be able to do something to work with this problem, we need to be able to put it in a form that we recognize. And when I say form, what do I mean? I mean exponential or logarithmic form. Alright, so we always have to get these problems in exponential or logarithmic form. We need to rework them somehow, and eventually, that's why I'm saying they'll boil down to exponential or logarithmic form. When we do that, then we can convert just like we did over here in part C. So you may want to write that down and star it. We need to get to be able to convert between the forms. You need to first make it into that form. So here it would be in logarithm. It would be in exponential form if we got rid of that 820. So we'll subtract 820 from both sides, and let's see what happens. So we get 10 raised to the 5 plus 2x is equal to 48780. And now this is exponential form. So just doing that one thing helped us tremendously, and it got us back down to something that we're already familiar with, or something that we know or have seen. So we know that this is our base, this is our exponent, and this is what's left over. This is exponential form. So there's nothing else we can do here other than convert it to logarithmic form, and pretty much our answer is going to pop out for us. So I know when we go to log form, there's going to be a log in there and an equal sign, and then my base is 10, but I don't write 10 because that's the common logarithm. We don't have to write it. It's implied if nothing's written that it's base 10. Then my exponent goes over here, 5 plus 2x, and then what's left over? And then what do we do to finish? Well, we need to get this x by itself. So we have a positive 5, subtract both sides by 5, so you get log, and be careful here, this is a common mistake. This is 48,780 minus 5. So if it helps, put it in parentheses there, this 48,780. This 48,780 is a parameter to this log. So if you were to plug this in the calculator, it would say log and open a parenthesis. Then you'd have to plug in this number and close a parenthesis. And then from this number, you subtract 5. That's very important that you keep this distinguished, and I will ask you this on the test, or something along the lines of this, and it's an easy trap. Alright, is equal to 2x, and then divide both sides by 2. So log of 48,780 minus 5 all over 2. And that would be your answer. I would, if it's helpful to you, I would just get in the habit of go ahead and put everything in parentheses like that. That's of your log function parameter. Okay, so let's look at this problem. And for some reason, this type of problem throws some students off. And I can kind of see why, but on another hand, it's working with the same type of, we're still working with logarithms. So let me just write it and be quiet. So 2,000 is equal to 18,000 e raised to the negative 0.4 t power. So if you recall, this is our compounding continuous formula also. We might look at a problem again later on that. But for now, let's just look at solving this. So anytime you have something that you can divide or add or subtract or multiply just to get rid of and simplify things, always do that. Dividing this 18,000 over just makes our life easier no matter what. Same thing over here. Subtracting this 820, it's just going to make our life easier. So just do it, and good things are probably going to happen. So let's just do that, and we have to, but it's also going to make our life easier. By doing that, we'll end up in a good place, and I'll talk to more about that in a second. So divide both sides by 18,000. And that's equal to e to the negative 0.4 t power. Now 2,000 divided by 18,000, you wind up getting 1/9. The zeros will cancel out and you get 2 over 18, and then that reduces to 1/9. It's best to leave a fraction. It's much more accurate than writing a decimal, unless it's a decimal. If it's a decimal that doesn't stop, then it's not very helpful. But the majority of the time, leaving as a fraction is the most conventional and accepted way, unless it's specifically said otherwise in the problem. Now here you might be thinking, how do I continue? And I encourage you to pause and try a couple different ways to try to get going. But on closer inspection of this, you notice that we're in the same position as we are over here at this step. Alright, this is just flipped. If we were to flip this, then it'd look the same as here. Our base over here was 10 with the exponent of 5 plus 2 to the x. Over here, our base is e with the exponent negative 0.4t. So the e, I guess, is what throws some students off. And then we're multiplying, and the exponent might be throwing you off. I'm not sure. So don't let that throw you off. Just realize that we're in exponential form here. And there are multiple ways of doing this problem. All of these problems, there's multiple ways of doing them. So don't let that throw you off. But what I'm trying to convey to you is, if you can recognize that this is exponential form and convert it to logarithmic, then there's only one way that there's a very limited number of things you need to remember to how to solve these. So if you can view this as exponential, which it is, then we can continue using that form, or converting it to logarithmic. If you're more comfortable with switching these two, because that's how we typically convert it, then go ahead. But I'm going to leave it like this for now. I know I'm going to log form, and there's a log in here with an equal sign. What's my base up here? My base here is this e. What is log base e? Do you remember? That's the natural log. So I will rewrite that here in a second, but for now I'll just leave it as that. Over here on the other side of the equal sign always goes my exponent, and then what's left over goes here. And then to get t by itself, we just divide both sides by negative 0.4t. Oh, first I'm going to change this log e to natural log. Some of you can do all these in one step. That's fine, but just for the sake of having good notes, I'm just going to write the extra step. And now divide by 0.4, negative 0.4. Natural log of 1/9 divided by negative 0.4. That is t. Connect math can get finicky. Sometimes it might want the negative up here or out to the side. Just try to follow along. If you do view an example, they might tell you how exactly they want that to be solved. Just be aware of that, and that's something that can happen. Alright, so what we're going to look at now is another equivalence property, this time for logarithmic expressions. And it's very similar to the exponential equivalence property we looked at. So just to recall the exponential equivalence property, expo equivalence. This is the one we just looked at the beginning of this video lecture. It said b to the x is equal to b to the y. That implies the exponents have to equal each other. So we're going to have something similar for logarithmic expressions, and it comes in handy when it arises. Equivalence property of logarithmic expressions. So I'm just going to call this the log equivalence property. I'm not just going to write log equivalence just to save us some time and board space. It's very similar up here. The only difference is now we're going to have log base b of x is equal to log base b of y. Can you tell me what that implies? If my logs have the same base, if I have the same base and there's nothing else over here, there's one log on each side and the bases are the same, that tells me that the insides or the parameters of those logs have to equal each other. X is equal to y. Alright, I think that should be pretty straightforward at this point, but let's do one example just to see what we get. And we'll call this example 2. We're just going to say solve again. Alright, here's part A. log base 2 of 3x minus 4 is equal to log base 2 of x plus 2. I didn't leave myself much room there. Alright, pause the video and you give it a try real quick. Okay, so I have a single logarithm on both sides. My base is the same, they're both 2. So that tells me that what's inside here, what's in the parameters section there, has to equal each other for these to be the same thing. So 3x plus minus 4 is equal to x plus 2. So see how that relates over here? Did the same thing. Now it's just solving for x. Add 4 to both sides. So you get x plus 6 over here. And then subtract x over on both sides. So you get 2x is equal to 6. And now you divide both sides by 2. X is equal to 2. Now what we're going to start getting into are similar problems like we just did. We're going to get into problems like we just did for the exponential and we converted to logarithmic. Now we're going to be starting in logarithmic form. And we'll have to learn how to manipulate these. And it's a little different, but in general they're the same. You need to boil it down. You need to get it into a form that we're familiar with and boil it down to the logarithmic form itself and then convert to exponential, and out will pop your answer. Part B. Four times the log base 3 of 2x minus 7 is equal to 8. And again, I want to stress that there are multiple ways to do these problems. I'm going to take the path that typically seems to be the most that helps students get these problems right the most of the time. So here, we have this 4 out front that we're multiplying to this whole thing. And so if you think back to what I said a few examples ago, if you have any extraneous information like that, like the plus 820 or the 18,000 that we're multiplying by, just get rid of it. So same thing here with this 4. Just get rid of it and then let's see what happens. So we're multiplying this side by 4. To get rid of it, we divide both sides by 4. So we get log base 3. 2x minus 7 is equal to 2. Now, what does this look like? This is logarithmic form. Like I said, everything boils down to logarithmic form or exponential form and then converting it. So here we're in log form, we need to convert to exponential. So my base is 2, my base is 3, my exponent is 2, and what's left over, or the answer, is there. So my base is 3, my exponent is 2, and what's left, it's equal to what's left over. And from there, it's something that we're very familiar with. This is 9. And then add 7 to both sides. And then there, divide both sides by 2. So 8 is equal to x. Alright, and how would you check to make sure that answer is correct? You take this 8 and you plug it in here, and you see if both of these sides equal each other. Which in this case they will. Alright, next problem, we are going to be part C. Part C will be, I want you to try part C by yourself. It's a pretty straightforward problem. similar to the one we just did. In fact, it might be even a little shorter, but give it a try. So that's a log of x plus 47 is equal to 2.6. So give it a try real quick. Alright, so we're looking at this and we see there's no extraneous things that we're multiplying by or dividing by or adding. So we can leave it like this. We need to recognize that we're in logarithmic form. This one's pretty straightforward. We're already in the form we need. All we have to do is convert to exponential and out will pop our answer. So my base here is not written, so that means it's 10. My exponent is 2.6, and that's equal to what's left over. Subtract both sides by 47. 10 raised to the 2.6 minus 47 is equal to x. And that answer is perfectly fine. And how would you check to make sure that this is the correct answer? You plug it back in up here. I keep reminding you of that because here in a few problems we are going to have to, we're going to get two answers and we're going to have to actually want to check to make sure that they both actually work. And we'll get to that actually in this problem next. So spoiler alert, my bad. So let's look at it. This one's going to take a little more room than normal. Oh, I might be okay. Part D. Log base 2 of x is equal to 3 minus log base 2 of x minus 2. If you want to try it, I encourage you to go ahead and try this one. What's going to happen is you'll just have to manipulate it a little bit, do some algebra, think about the properties that we used in 4.4, and then eventually you'll boil it down to logarithmic form, and when you're in logarithmic form you convert it to exponential. So please try it if you feel comfortable doing so, and if not, still give it a go. You learn from failing. Alright, so this one is a little different than anything we've seen so far. We can't use the logarithmic equivalence property. We do have a log on both sides with the same base, but this 3 and this minus is really messing with us. So that's not allowing us to do anything. We have to think back to section 4.4 here, and we have to get a little creative. So what I'm going to do first is I'm going to take this minus log base 2 of x minus 2 and I'm going to add it to both sides. And so I get log base 2x plus log base 2 x minus 2 is equal to 3. So only thing I did was take this and move it over to the other side. Now, if you remember back to 4.4, I kept telling you that you're going to have to just recognize when you see these properties. And so here, if you recognize you have logs with the same base and you're adding those two logs together. Remember, you can go back and forth. And with those properties we learned in 4.4, we learned the product property. If you're multiplying two things inside of the parameter, then you can break them apart into two different logs and add them together, which is the case we have here. The quotient property, if you had log and you're dividing two things inside of the parameter, then you can break them into two different logs and subtract them. So here we have logs with the same base and we're adding them. That means we can combine them and multiply these two together under one log. So this is log base 2 of x times x minus 2. And I'm going to use brackets just because too many parentheses gets confusing. So, but this x times x minus 2 is the parameter inside of the log 2. So look at this, and if we were to apply the product property, you would get this. So you just have to be able to go back and forth. That's why in section 4.4 we looked at expanding and condensing, because all that's going to be very helpful in here. And this is still equal to 3. Now, I want you to try to pause the video and finish it from here. Alright, so I hope that you recognize that we are in logarithmic form. Go back and look at part A, B, C, not A, I guess B and C, and realize that this is logarithmic form. Like I said, everything's going to boil down to logarithmic or exponential form and then converting it to the other. So now my base here is 2, my exponent is 3, and that's equal to what's left over, x times x minus 2. Alrighty. And if you were to multiply this out up here, that's fine. I'm just going to save it to do it down here. That's not really a huge deal either way. So I'll just do it now. This becomes 8 equals x squared minus 2x. So remember, all we're doing is distributing this x. X times x is x squared. X times negative 2 is minus 2x. And what is this starting to look like? If we need to rewrite it a little bit, but hopefully it's starting to look somewhat familiar to you. If I subtract 8 from both sides, then I wind up with 0 is equal to x squared minus 2x minus 8. This is quadratic formula, or quadratic form, which means we have to do the AC method. And I'm going to assume we're all okay with the AC method at this point. So I'm just going to write the answer. It's x minus 4 and x plus 2. That's equal to 0. The equal 0 was on this side, and I just moved it to over here. It doesn't matter which side. You can flip-flop as long as you flip-flop everything on both sides of the equal sign, you're okay. And so I'm going to go to the other side of the board and finish this. So you can already see here that we're going to get 2 answers. You get x minus 4. I'm going to rewrite that last step. So you're multiplying these two things together, and they're equal to 0, so you can set them separately. Equal to 0. And this is what you get. And then on the left, you get x is equal to 4, and x is equal to negative 2. So what would happen here is typically you would just move on and say, yeah, those are both our answers. But here you have to be careful because they're not both not our answers. What we need to look at, we need to plug both of them back in and plug them both back into the original equation up here and see if both sides actually do equal each other when we simplify. Now I'm going to let you in on a little secret here. Go ahead and try x equals 4, and you'll find out once you do that work that it does work. So you just plug 4 in here, plug 4 in here, and just start simplifying both sides, and you'd see that both sides would eventually equal 2. Alright, 2 is right. But the secret here is, and I didn't really talk about this because it's not really a huge issue right now. But so if I plug in negative 2 up here, so let's do that. Log base 2. I want to rewrite the problem here. And this is kind of a shortcut, what I'm about to show you. but it's pretty handy. So now I'm going to plug in 2 here. So log base 2 of -2. I'm going to plug in -2, excuse me. 3 minus log base 2 of -2 minus 2. So you cannot have, and here's the secret to this, or the easy trick, you cannot have a negative number inside of any logarithm of the parameter section there. That number always has to be greater than positive. So that right there tells me that -2 does not work. And this just so happens to be -4, so which is fine. But as long as one of the logs have a negative inside of its parameter, then that answer will not exist, or it doesn't work. Excuse me. All right, so let's look at one more example here, and it's going to be a finance example. So we're going to go back to a couple sections ago. And this is a good problem to look at because it's a good review problem too, because it encapsulates several different things. Example 3. Let's see, a couple invests $8,000 the expected yield is 4.5% compounded monthly. How long will it take the initial investment to double? Alright, so a couple invests $8,000. The expected yield is 4.5% compounded monthly. How long will it take the initial investment to double? So the first thing we need to know here is the formula. What do we use and what do we plug in? Well, we know we're compounding monthly, so that tells us that we're using this formula. A is equal to P times 1 plus R over N raised to the N times T power. Alright. And from here it's just plugging in the things that we already know. So well, let's just plug in what we know. A is here. P is the principal or the starting amount, so that's 8,000. And then that's this 1 plus is here. R is the interest rate, which is 4.5%. But remember, we have to move the decimal over 2 places whenever we're dealing with a percentage. So it's 0.045. That's what we need to plug in for the rate. 0.045, all divided by N, which is the number of times you're compounding per year. So this is compounded monthly. How many months are in a year? 12. Raised to the N times T power. So that's 12 times T, which T we don't know because it says how long will it take the initial investment to double. So T is actually what we're looking for. That means we need to figure out what A is because we're trying to find T. So what would A be? Remember, A is the accumulated value. So how much do we want to accumulate over T years? We want this initial investment to double, this $8,000. So for that to double, that means A would have to be 16,000. So I'm going to write that on the other side of the board. 16,000 is equal to 8,000. 1 plus 0.045 over 12 raised to the 12t power. Alright, how to proceed from here? Well, we have this extraneous 8,000. We could divide both sides by that and it would make things look a little prettier. So let's do that. I don't know where this is going, but let's just do that to see what happens. So we divide both sides by 8,000. So 16,000 divided by 8,000 gives you 2. That's equal to 1 plus 0.045 over 12 raised to the 12t power. Alright, so I'm going to show you a new way of solving one of these types of problems. And the way I'm about to show you, you can actually use it on several of the problems we already worked tonight. So, do the homework, look through its examples, and see which way you like best. But in some cases, and this one in particular on this example, what I'm about to show you is what I think is the simpler way to do it. So as long as we can do the equivalence property for logarithm expressions backwards. That said, if you have the log base b of x is equal to log base b of y, then that is equivalent to x equals y. So what I'm proposing that we do here is sorry, this is getting in my way. What I propose is that we're here. We're at x equals y. This is x equals y. And what I want to do is I want to add a log base b on both sides of this equation. And so it doesn't change anything as long as I do the same thing to both sides. And so I want to choose the base to be e, which means it's ln. So I'm going to do ln to both sides. So natural log of 2 is equal to the natural log of 1 plus this whole thing. And we could have did this on a couple problems tonight. So just depending how you want to look at it. But here, this one is a little bit easier doing it this way. Alright. So now the question is, why do I want to do it that way on this problem? Or why would you want to do it on any problem? Well, what it allows you to do is use some of the properties from 4.4. Now we have this natural log and we have a power up here. And this power contains our exponent that we need to get out of there. So now that we're in a log form, we can use the logarithmic properties to use the power rule, take that 12t to the front of this term. So now we can move this 12t to the front of here, and now we're multiplying it. So you get the natural log of 2 is equal to 12t times the natural log of this whole thing. Alright. It's supposed to be 12. And so it looks a little funky what we have written here. And just to make the next step, what I'm going to do a little bit clearer, I'm going to, and especially clear in your notes, that when you go back and read it, hopefully it makes a little sense. I'm going to write another step here, and all I'm going to do is switch this 12 and this t. I can do that because I'm doing 12 times t times this natural log. If I'm multiplying everything on one side, then I can interchange where I'm multiplying things. So the natural log of 2, and it's just going to make my next step after that a little bit clearer. So just follow along. So t times 12 natural log of 1 plus 0.045 over 12. Now to get t by itself, all I have to do is divide both sides by 12 natural log of this. So that's why I wanted to switch these two, so you can see that I'm actually just dividing by this thing on both sides. Sometimes it's a little confusing saying I'm dividing by 12 natural log when I'm kind of skipping that t there. So I just wanted to kind of emphasize that it's okay. So now I can say the natural log of 2 divided by 12 natural log 1 plus 0.45 over 12. I missed a 0 there. Is equal to t. And so in this problem, on exams and Connect Math, they may actually, I'm fine with this answer because it's more it's more exact, it's more accurate. But on this type of problem, typically you would want to give an answer, and it would be approximate. So this means that t is approximately 15.4 years. T is approximately 15.4 years. So that means your investment of $8,000 will double itself in 15.4 years.